Okay, so um, continuing with what we talked about on Friday, dealing with binomials, and we talked about the formula, and we talked a little bit about putting it in the calculator to do this. We're going to finish talking about how, because there are specific ways to put this in the calculator, because the calculator treats this as a very specific distribution when it does the calculations for it. So we're going to go over that, and we're also going to talk about mean and standard deviation of a binomial. Okay, so just as a reminder, PDF is for singular probability. So if you're doing a binomial PDF, that has to be for a very specific singular probability that you're working with. The binomial CDF calculates cumulative probabilities. And remember, we talked about this, it goes from left to right. And here's the thing, it includes the number that you put in as your X, which is your number of successes. Okay, so if you want something to be included when you're doing your binomial CDF, then you need to make sure that you're actually putting that number in when you're doing a less than or equal to. Okay, so basically what that means is when you're doing or dealing with a binomial CDF, it's automatic. It's sort of like when you reset your calculator and it automatically goes back into like radian mode, right? Or turns off the diagnostic for our regression. The default for a binomial CDF is always going to be a less than or equal to. Okay, it goes up to and including the number that you put in. So if that makes any kind of a sense as far as that goes, we'll say that the default is less than or equal to. Okay, so that's for a binomial CDF. Okay, and that's where we got to on Friday. So we'll talk about how to do these other ones, because obviously not all of our, probabilities are going to be less than or equal to. It doesn't work that way. Okay, so in the calculator, what we did on Friday with the type O blood, the probability of X being less than or equal to 2, right? Less than or equal to 2 children with type O blood with 3 trials and a 25% chance of success. The way it would get put in the calculator is binomial CDF, right? You do your trials first, that's N, and then P for your probability of success, and then X, how many successes you want, right? That's always the order that it goes in. Whether you're using the big calculator or the small calculator, it's always N, P, X, okay? And if you're using the skinny calculator, it actually asks you, if I'm not mistaken, in that order for those specific things. Yeah, trials, p-value, x-value. So it does ask you in that order. If you're using the bigger calculator, the ones from class, you're going to have to remember that it's NPX because it's not going to tell you. Okay, it's trials, probability, successes. All right, so that being said, with the default being less than or equal to, meaning that it has to include the number you put in, what if we want to do a strictly less than? Okay, if we don't want to include 2. The big thing with the binomial distribution is that your number of successes are always whole numbers. Okay, so you can have, in the case of 3 children, how many of them have type O blood? You could either have 0, 1, 2, or 3, right? So that's always, your number of successes are always going to be whole numbers. So it actually is not too bad. So basically, what would mean the same thing? What inequality? Okay, so we're looking for an inequality that means the same thing as less than but not including 2. Right, we need a probability that means, or not a probability, an inequality that means the same thing as less than but not including 2. And since they're all whole numbers, I hope some of you said it, it is really the same thing as less than or equal to 1. Okay, think about that for a minute. If you were to have the probability distribution that we did on Friday, it was like 0.42, 0.42, 0.14, 0.02, something like that. If you had that and you were trying to figure out a probability just using the table, if I wanted x strictly less than 2, then I would add up 1 and 0. Okay, so in your calculator, you would put it in as a binomial CDF 3.25 comma 1, because that's the number that it's up to and including. Okay, and remember, the only reason we're even going over how to do this in the calculator is because if it was a small distribution like what we talked about on Friday, it's not really a big deal. There's only like 4 choices. But if you've got something that's got like 10 different possibilities of success, you don't want to calculate all that stuff by hand. It's annoying, okay, and then have to add them all up. And it takes way too much time, okay? So that's the only reason that we're learning how to put this in the calculator and learning all the little tricks for it. Go again, picture x is less than 2 if you were looking at your table, what you would actually be including. Basically 1 and 0. Okay, and just realizing that when you do the binomial CDF in the calculator, that's how it works. It includes the number you put in. Okay, so that being said, let's try a greater than to see what happens. We already know that we have to subtract it from 1, but we need to understand what it includes, what it doesn't include, how that we can get the calculator to actually calculate it for us. Okay, so we're still looking at 3 trials, 3 kids, 25%, probability of x greater than 2. Okay, what numbers, if we were looking at just our table, would that include? Well, that would include not 2, strictly greater than 2 would include 3, and that's it, right? That would be what our table, if we were to actually pull it off of our table, we would only be looking at the outcome for 3. So as a probability, okay, as a probability, that would look like 1 minus the probability of x being less than or equal to 2, right? Because it actually does include it, right? If we were to think about that, this takes 2 and everything below it off. We subtract it from 1 and we get everything that's above it. Okay, what does it not include? Well, everything greater than 2 does not include 0, 1, or 2, which is how that probability would come from. So how would you actually put that in the calculator? Well, using the binomial CDF. Okay, so 1 minus binom CDF. All right, and since it covers everything up to and including, what number do we need to go up to and including out of our 3 trials and a 25% probability? Well, we need to take off everything up to and including 2. Because that would take care of 0, 1, and 2. Subtract it from 1, we get the only piece that's left, the 3 from our table. All right, so let's try a greater than or equal to. Okay, so greater than or equal to 1. Well, what numbers from our table, again, our same table, does that include? That includes 1, 2, and 3. Okay, what does it not include? It does not include 0. So I need to find a way to basically capture 1, 2, and 3 and take off 0. Now, I mean, pretty much you could find the binomial CDF, right, for 0 and subtract it from 1, or not binomial CDF, binomial PDF for 0 and subtract it off of 1. That would work because you are only not including the 0. But since we're trying to do this, see how this works with the CDF, it is going to be 1 minus, I'm going to type this, binom CDF. Okay, so trying to write that is fun. All right, so what am I going to put in that I'm trying to get rid of from my set? If I want everything from 1 and above, I'm taking off whatever's below it, right? So again, 3 trials, 0.25, that never changes. So the only number that I really want this thing to include, or where do I want it to stop, basically, because that's, remember, it is counting all the way up to and including that number. I want it to stop at 0. So if it's a greater than or equal to, I need it to stop at 1 less than that number. Okay, there is kind of a little pattern to it as far as how it actually works. If I'm doing a strictly greater than, then I do 1 minus up to that number. If I do a greater than or equal to, then I do 1 minus all the way up to one number less. And again, it's kind of like a logic puzzle. You really have to think about what it's including, what it's not including, so that you know what to take off if you're doing a greater than or equal to. Okay, so let's try some of these in a calculator using the binomial CDF. And we're going to up the stakes a little bit. We're not going to be dealing with 3 trials. We're not going to deal with a family of 3. We're going to deal with a family of 5 this time. But same probability and the same types of questions. But we're going to do some different ones as far as, you know, PDF, CDF, see how you set this up or see how well you set this up. So go ahead and write this down. And first try it with exactly 3 children out of 5 having type O blood. All right, so you're set up for an equal to. Remember, an equal to is a PDF. 5 trials this time, probability is 25%. This is how you would handwrite it. Right? This is how you would do your 5 and then go to math, PRB, and find the NCR. Okay? And I want 3 successes and 2 failures. And that's the way you would show the formula as far as showing work for it. Putting it in the calculator, you're going to use your distribution menu, binomial PDF, 5 trials, 25% probability, 3 successes, and that should give you, I thought I put it in. Guess I didn't. Bad. Okay, so that should give you 0.0, we'll just call that 0.088. Okay, so 0.088 or 8.8% basically. Okay, again, that would be a binomial PDF with 5, 0.25, 3. Nope, not 4, 3. Right? That should be the setup for that. Okay, so let's do a couple of different inequalities just to see. Again, same probability, same trial number. So how does greater than 3 get set up? So again, think about what it is you're including. If you were to have done out the whole table, you would be including what? 4 and 5 only, right? Not actually including 3 at all. So if I want 4 and 5, then I'm getting rid of 0, 1, 2, and 3. So you're set up. 1 minus a binomial CDF of 5 trials, 25% probability. What am I getting rid of? 0, 1, 2, and 3 being the highest number that I'm getting rid of. So that's what I need to up to and including. So that's what you're going to put in your calculator. And you should have, if you did not already, gotten, let's see, binomial CDF, 5, 2, 5, and 3. Should have gotten 0.01, we'll call that 6. 0.016. Okay, so rounded about 1.6% chance of having more than 3 kids with type O blood in a family of 5. All right, so let's try a less than or equal to. Okay, so again, what am I including in this one? I'm including 0, 1, 2, and 3. So I'm pretty much everything that I left off of the other one would be there. So since this is a less than and we start counting from left to right, this one actually just goes in as a binomial CDF. And again, 5 trials, 25% probability, and I want up to and including 3. So that should be let's call that 0.984. 0.984 or 98.4%. Okay, so again, just practice, and you will be doing some of these tonight. I've got some picked out of the book for you to practice on just to make sure, and I'm going to make sure I give you some odd and some even so you can check the answers in the back of the book for the odds to make sure you're setting it up correctly. Okay, so onward and upward. We need to be able to calculate the mean and the standard deviation of our distribution. Now keep in mind, this is pretty much a probability distribution, guys. We could make a table out of this. It just takes a little bit of time. You could make a table out of this, and then you could go and do the multiply, each outcome times its probability and add them all together. Or, we'll get to the shortcut as far as the formulas, but I'm going to make you do it the long way first. So, mean and the standard deviation. Okay. We already know this formula. We're going to use the PDFs to get our table, and we're going to actually find the standard deviation, and then I'm going to show you the shortcut and the formulas for it if you didn't already get them from actually doing the reading in section 6.3. Okay, so we already have this part. Okay, we're going to use that same formula we've been doing. In our family of 5, the probability of having 3 children with type O blood was what? 0.088. Okay, I'm going to give you 2-3 minutes. Remember, you don't have to keep retyping this thing in. You can just go back and change your number of successes that you want. I'm going to give you a couple of minutes to go and fill in this table. Right, we've already got the, not that one, that one, 0.088. Okay, so go back and do your binomial PDFs. And again, all you have to do is just change your number of successes. Take 2 minutes, go back and fill this chart in. And then I want you to find the mean, either by putting this in your calculator and doing one variable stats, right, with the list 1 and list 2 for your probabilities, or going and actually multiplying them out. Okay? So, well, you know what? Put it in the calculator and do list 1, list 2, because I do want you to find the standard deviation as well. So take a couple minutes, fill those in. I'm going to do the same thing. So that way you can have all of them and we can run one variable stats on it before I show you the shortcut. Alright, so 5 trials, 25%. And please go to 3 decimal places to make life easier. Okay. All right. So again, not having to go back and do this over and over and over again. You're just having to change your number of successes. You should have gotten 0.237, 0.396. Remember rounding to 3 decimal places, please. 0.263, 0.088, 0.015. And yeah, I know the scientific notation says like 3 zeros and then a 9, so we're going to round again to 3 decimal places. So 0.0009 is actually 0.001. If you add that all up, it does actually equal 1. So if we round to the 3rd decimal place, that usually gets it to be the most accurate as far as getting our distribution to actually add up to 1 like it should. Okay, so go ahead and run one variable stats and see what you get for the mean and the standard deviation. And again, we're just going to go ahead and round to 3 decimal places. Okay, so your mean, 1.25. Oop, I made an oopsie. That should be 1.252, shouldn't it? Let's make sure I have my numbers right. 237, 396, 0.263. No, that should be 0.264. That was my oopsie. Okay, 0.264. So that should be 0.252. And rounding to 3 decimals on that one. Stat calc. Let's make sure I didn't mess that up. 1.252 and 0.969, actually. There we go. 0.969. Okay, so there is your mean and your standard deviation. Now, again, we could do this the old-fashioned way, 0 times 0.237 plus, each pair going down the line. And also the fact that, having to get that whole table in order to find the mean and the standard deviation, if we don't want to, maybe if we don't need those individual probabilities, right? And if all we need is the mean so that we can talk about it, or the standard deviation, we have a shortcut. Okay? This is the way this works. For any binomial, and this is on your formula sheet, and you need to understand, again, this only works for binomial distributions. Okay? It's a very specific formula for it. The mean of the binomial distribution is your number of trials times your probability. Okay, and again, obviously it's going to be a little bit off as far as not as exact with the decimals, depending on how far out we run it. But if 5 is our number of trials and our probability is 0.25, then lo and behold, 5 times 0.25 is equal to 1.25. So you're not going to get counted against in an open response question if this is how you show finding the mean of a binomial instead of going through the whole table and running one variable stats on it. Okay, it actually does count. Now, I'm going to do the standard deviation first, simply because that's the one we deal with the most, not the variance. Standard deviation is, that's supposed to be on there. Let's try that again. It is NP times 1 minus P. The big thing is that what's the difference between variance and standard deviation? What do you normally have to do to the standard deviation to finish off the job? And I don't know why that's not on here. I think I made an oopsie when I was drawing it. it is the square root of that. Okay, it is the square root of the mean, NP, times the probability of failure. That's pretty much what 1 minus P is. And if you take the square root of that, again, we can approximate it. That's going to be the square root of, okay, so 5 times 0.25 times 0.75. Okay. So let's try that and see if it comes close. 0.5, oops, not 0.5, 5 times 0.25 times 0.75 and a square root is 0.968. So that is really, really close. Okay, and that's really close as far as taking it all the way out to 3 decimal places to run the one variable stats on. So again, either way would get you a correct answer. If you're given the distribution, there's no reason not to put it in your calculator and run one variable stats. But if all you're given is your sample and your probabilities, this is a really nice formula that works. We're not going to go over why it works because we would have to go through like the entire standard deviation formula and simplify it. And I'm not doing that today. But it does work, okay? And this is actually in your formula sheet. Now, again, the only difference between standard deviation and variance is the lack of a square root. So that actually, yes, the lack of a square root because standard deviation has to be square rooted and variance does not. Okay, again, the two most that we'll be looking at are mean and standard deviation. Okay, so and that is how we find it. So let's practice and play with this and see what we can do. Okay. One of the big ideas for binomial, you absolutely do have to write this down. I'll give you a couple of minutes. This is very, very important. And this is this ties directly into the testing that we'll be doing after Christmas.
Can we get the booklet for you?
Okay, so the last part for binomial distributions is that we know that the trial, I mean, that was literally the bins, right? BINS. Each trial must be independent, okay? And we talked about this on Friday. That means that if you're like pulling cards out of a deck of cards or buttons out of a bag or whatever, we have a rule for that. And that's that you always replace after selection. Okay. And I just put an example over there, like marbles in a bag or buttons in a bag or cards out of a deck. We always put them back, okay, in general terms. Now, here's the fun part, not in general terms. In the real world, okay, if we're using a simple random sample, which, that's our best bet, right, when we're talking about a population. If we use a simple random sample, okay, and we're talking about people, that means we select without replacement, right? You can't have the same person twice, right? You can't pick the same person twice. So how do we get around dealing with the fact that we have to have a simple random sample? I mean, it has to be random. That was one of the big rules that we have as far as sampling. Anytime we're doing a sample, even when we're trying to do experiments, we always had to have random assignment at least, right? We have to have that randomness. So how do we get around that and still be able to use binomial in the real world? Because otherwise, binomial would be pretty much, not that. Binomial would be pretty much limited to talking about dice and coins and cards, and it doesn't do us any good. We need it to apply to the real world. Okay, so we get around that by making sure that our population is large enough. Okay, and we're going to talk about how large is large enough. So that your sample is also not more than, and I told a bunch of you this when you were doing your projects, that you could not take more than 10% of your population anytime you take a sample. Okay, so if your population is big enough that when you take 10% of it, and I'm about ready to show you the rule for it, that when you take 10% of that population, it follows this rule, then we can still use binomial to talk about people. Okay, so please keep in mind also, I want you to specifically remember that this is for proportions. Okay, that this is not for anything else. Remember that a probability and a proportion is about the same thing. It's a part of a population, right? Okay, so this is specifically for proportions. Normal approximation, meaning that it's still going to, it's really not the normal approximation, it's more like the independent approximation. So n being your sample size has to be big enough so that basically your mean, right? That's your sample size times your probability, right? Has to be 10. So you have to have 10 successes because that's basically what your mean is. And you also have to have 10 failures. That's what that is, because it's your sample size times or your number of trials rather, times your failures. So we call this 10 successes and 10 failures. Okay. That means that your population has to be big enough, okay, to give us a sample size, right, that follows this and is still not more than 10% of your population. Let's see if I can break that down further. The very smallest amount, obviously, for your sample size is going to have to be 20, right, in order to get 10 successes and 10 failures, right? And if you have a population of 20, right, 20 times what gives you 10? 20 times what probability would equal 10? Just out of curiosity. Okay, yes, your probability would have to be 50%, right? You'd have to have a 50% probability to have that small, 20, of your trial size, right? Okay, so that means, or of your sample size in this case, sample being the same as basically the trials, that means that you're always going to really shoot for more than a trial size of bigger than 20, right? Especially if your probability is off of 50%. Like what would happen? What would happen if P was like 20%? Okay, how big of a trial, or an n, sample trial size, would you have to have to still get, 10 successes and 10 failures? So how big would n have to be? Well, again, you're answering the question, what times 0.20 gives you 10? Well, let's see. 10 divided by 0.20, if we're solving it algebraically, that's 50. Okay, so I want you to understand something, all right? The further off of 50% your probability is, right, your chance of success is, the larger your number of trials, which is i.e. the same thing as your sample size, is going to have to be, okay? Because you have to ensure this so that we don't get in trouble with that non-replacement rule, okay? If we don't have this, then we have an issue because we're sampling without replacement, and it's going to mess up the data. It's actually going to mess up the independence. It's going to mess up all this kind of stuff. So this is one of the big ideas that you need to carry with you until next semester, because we'll be seeing it more and more and more. But you have to have more than 10 successes and more than 10 failures when you're working with stuff, okay? So you should be able to work algebraically to figure out how big a sample or trial size you need, and you should also be able to work algebraically to figure out what your probability would be to make that 10 and 10 rule work, okay? So it's one of the big ideas for binomials. You do have an assignment that I'm going to send out in Remind, and it has to do with finishing reading section 6.3 actually, and some practice problems on the binomial, and then we'll get to geometric tomorrow, and that should be it. Have a good afternoon.